Welcome to this video guide to the key features of Sparkvue software used to collect data from PASCO wireless sensors across the certified PASCO version of OpenSciEd high school curriculum. 15 lessons use Sparkvue software in student investigations and teacher demonstrations. See the resources provided in these lessons for instructions specific to that lesson's Sparkvue-based activities. This video provides a general orientation to Sparkvue features used across multiple of those activities. The most straightforward use of wireless sensors is to simply monitor measurements. While some sensors have a built-in display, any sensor can be connected to Sparkvue software to view its live readings. Launch Sparkvue, and from this welcome screen, choose the sensor data path. Next, connect your sensor. Power it on, and notice that its Bluetooth light blinks red, indicating that it's available to connect to. In Sparkvue, select the Bluetooth button to open the Wireless Devices dialog. If you're using the traditional installed Sparkvue application, you should see your sensor appear here automatically under Available Devices, with its 6-digit ID shown in Sparkvue, matching the ID printed on the sensor itself. Select your sensor to connect it to Sparkvue. If instead you're using the browser-based Sparkvue PWA or Progressive Web App, select this Connect a Wireless Devices button to open the browser's Bluetooth dialog. Select and pair your sensor here to connect it to Sparkvue. In either version of Sparkvue, press Done to return to the Sensor Experiment Setup screen, with your sensor now connected, as indicated by its Bluetooth light blinking green. By the way, in activities that use multiple sensors, just repeat the connection process for each sensor. The measurements available from the connected sensor are listed in this left column. Ensure that the measurements of interest are checked. In this case, just the sensor's pH measurement, already selected by default. Then, select a desired display template in the upper right to specify how you'd like to view the selected measurement. This activity uses the digits display template, which I'll select, to create a Sparkvue file with that display for the unitless pH measurement. Press the green Start button to begin data collection and view live measurements in the display. Press the red Stop button to end data collection. Other activities use Sparkvue to record and visualize measurements over time, often in graph display. Many of those activities specify a Sparkvue experiment file to be used for data collection. Each Sparkvue experiment file has been configured for the specific activity, so all you need to do is connect a sensor and you're ready to begin collecting data. Download these Sparkvue files to your computer from a lessons page in PASCO portal. From Sparkvue's welcome screen, again, choose the sensor data path and connect your sensor as before. At the bottom of the screen, select Open Experiment File, then Open from Device, and direct Sparkvue to open the experiment file you downloaded earlier. This particular experiment file is configured to show the CO2 concentration over time in this graph. The current reading from the sensor is shown here in the live data bar, helpful for checking the measurement during setup before you begin data collection. press the green Start button to begin data collection. This experiment file includes an initial 30-second delay to allow the sensor reading to stabilize in the bottle. Once recording begins, each dot in the graph represents a reading, recorded at the rate specified here, in this case 1 Hertz, or 1 measurement every second. Some experiment files are configured to stop data collection automatically after a specified time. This file will automatically stop recording at 10 minutes, so I'll fast forward to near that experiment time, and without my pressing the stop button, Sparkvue ends data collection automatically. You may have noticed during data collection that Sparkvue automatically scaled the graph to ensure that all the data was always visible. Here in the graph toolbar, you can scale the graph at any time so that the data fills it entirely by pressing this Scale to Fit button. In this investigation, students determined the CO2 concentrations at 1-minute intervals. I'll change the units of time on the x-axis from seconds to minutes to make that easier. While students could read approximate values from the graph axes, the Coordinates tool provides a more accurate method. Press the Coordinates tool button in the graph toolbar to add a Coordinates tool to a data point somewhere in the middle of the graph. The Coordinates tool label shows the x and y coordinates of the data point under the gray box. Drag the gray box to another data point, or use these arrows above the label to nudge it from point to point. Add as many coordinates tools as you'd like. All the data recorded between start and stop comprise a run of data, which the graph legend shows to be named Run 1. Although this experiment has each student group record only 1 run, other activities will involve multiple runs of data recording. To record another run of data, simply press Start again. Recording of Run 2 begins, as shown in the graph legend. Most Sparkvue graphs are configured to show only 1 run at a time, so when you press Start to record an additional run of data, prior runs are hidden. However, you can make any run visible with its Show Hide Eyeball icon in the graph legend. With multiple runs visible in the graph, be aware that graph analysis tools apply to what's called the active run, indicated by a red box in the legend. Make a different run active by clicking on its run symbol in the legend before turning on a graph analysis tool. Sparkvue files provided in PASCO portal help students get to data collection and analysis quickly, especially in more sophisticated investigations, such as this one measuring the braking force and corresponding stopping time for a wireless smart cart using its built-in force and position sensors. We'll start with my wireless smart cart already connected to this investigation's Sparkvue file. This Sparkvue experiment has multiple pages. Move to the Force versus Time page by selecting its tab. Before recording force data from the smart cart, with no force applied to the hook, click on the force measurement in the live data bar and select 0 Sensor Now to define the current reading as 0 newtons. Use this graph of force versus time to determine the average braking force as the cart is pulled by its hook through this friction accessory at a constant speed. The Graph Toolbar's Statistics button provides a choice of analyses for the force data. Select Mean to determine the average force over the entire run. To find the average force only when the cart was being pulled through the friction accessory, add a selection box from the Graph Toolbar. Adjust the box's position and size as needed to highlight only the data points of interest. The mean updates to analyze only the highlighted data points inside the selection box. So, the average braking force was 1.45 newtons. Students record this value on paper and later transfer it to the table on the experiment file's final page for further analysis. Edit the left column's measurement name to braking force, with a unit of newtons, and enter the determined average value in the first cell. To measure stopping time with this braking force, place the smart cart on the ramp up against the end stop, which sets a repeatable starting point. Navigate to the first page in the experiment file for a graph of the cart's velocity versus time. Record a run of the cart rolling down the ramp and coming to a stop with the friction accessory. Adjust the graph to better view the section of data corresponding to the cart coming to a stop. Scale the graph axes manually by clicking and dragging on an axis scale to stretch or compress it. Move the graph by clicking and dragging in the middle. To determine the stopping time, begin by placing a coordinates tool on the point when the cart first encountered the friction accessory. Click the coordinates tool label to reveal the delta tool, delta for change, to create a second gray box that you can drag to a different data point. The delta tool reports the difference in x and y values between the two data points. In this case, delta t on the x-axis is the stopping time for the cart, 0.152 seconds. Back on page 3, enter the stopping time in the corresponding cell to begin graphing the relationship between stopping time and braking force. Saving a Sparkvue file preserves everything about it, including recorded data and any analyses, allowing you to reopen it in the future to record more data or perform further analyses. To save a Sparkvue file, go to the main menu and choose Save. I'll open another file in which I've already recorded 7 sets of braking forces and corresponding stopping times. Shown here in the graph. To determine the relationships between graphed variables, turn on the graph's curve fit and select a fit type to apply it to the graphed data. We hope this overview has provided a helpful orientation to the Sparkvue features used across multiple high school activities. Don't forget to look to the written or video procedures for a specific activity for detailed instructions, including on using any specialty Sparkvue features beyond those covered in this video. Also, for additional assistance, visit the Sparkvue Online Help Center or check out the professional learning and support sections of PASCO portal. Thanks for watching.